All right, good afternoon, everyone. We're back at it, but it's Thursday, so the weekend is just around the corner. Good for us, right? Related rates, what do you think? Try that homework. You run into some issues at all? I mean, it's takes some getting used to, yes?
Yeah, I'm getting used to it. I think I did like about 10 questions, so
Okay, good.
I'm feeling good about it.
I'm going to do some more today. I'm going to try and do 4 problems today. Let's see how it goes. And then if I finish them, I might start 3.1, 3.2 today. We'll see. Here we go. So I asked you to look at this problem with the plane flying over with the angle. And I'm going to go ahead and work it out, okay? Because it's very similar to the problem that we finished at the end of class last time with, here it was, the plane flying overhead. We had drawn this picture here. It's pretty much the same setup, except what we're given, kind of what we want. These things might change. So let's just go at it here. So I'm not going to read through the whole problem again. I hope that you understand what's happening here. At the exact moment in time, we've got the ground, we've got the radar station, we've got the plane. We know that the plane is 2 miles high. That never changes. And we're talking about an instant in time when the moment in time is when the plane is 6 miles from the radar station. So that would be the distance from here to here is 6 miles. That's kind of the information we're given about the instant in time. The general picture is the radar station, the plane. The plane is moving, right, at 600 miles an hour. And what we're interested in is knowing at the exact moment the plane is 6 miles from the radar station, how fast, that's a derivative, the angle, the derivative of the angle is changing, all right? So I need to somehow represent the angle that I'm looking for in the picture. So if I connect these two together with a line, and let's call that H. H is changing, right? H is changing as the plane moves. H changes, but the angle that we're referring to here is theta. And we could also imagine that this could be like a right triangle, right? And we know that this side, very important, this side over here is 2 for sure, never changes. So who's going to help me with what I'm given and what I want? What am I given? The rate of change of something. I want the rate of change of something.
We're given dx dt. Well,
dx dt.
Yes, assuming that the 600 miles per hour is on the x-axis.
That's right. So we are going to have to label this side x. And this is what I talked about last time, that if you were to draw a line straight down from the plane to the ground, that black point is moving across the ground at the same speed that the plane is moving across the sky, because they're parallel to one another. So the rate at which x is changing with respect to time would be 600, but because the x is shrinking, I need to put negative 600. Can I clarify that at all? Are there any questions?
I'm sorry, when you say it's shrinking, is it because it's getting closer?
It's because the x in the picture is getting smaller, right? As the plane moves from left to right, that x gets smaller.
Okay, that makes sense. Thank you.
Okay. If the plane was moving from right to left, then we would say dx dt is positive 600. Okay, now we want the rate at which the angle is changing. So that's why I labeled that angle theta. I'm going to put d theta dt. And we want that when? At what moment do we actually want to know how fast the angle is changing? When what is what?
Was it H is 6 miles?
Exactly. We want to know it at that moment that H is 6. So now we just need to connect the variables together. Here's the part that is different than the last problem. Well, this is different from the previous problem with the same plane. We want to connect X and theta together. What do you think? Any equation you can think of that has a relationship between X and theta.
Is it, oh shoot, is it sine or cosine? I don't remember. But
Okay.
it's opposite over the hypotenuse, which I think is cosine.
So you're saying sine or cosine? Let's see. Sine of, if I were to write up here, let me just write it down up where you can see it. If I write sine of theta by definition is opposite over hypotenuse. So that would be 2 over h, right? That's, if I take a right triangle, sine by definition is opposite over hypotenuse. So the opposite side from theta is 2, the hypotenuse is h. Is now this equation definitely has theta in it, but does it have x in it?
No.
No, it has h. And so I know if I differentiate this, I'm going to get a dh dt. And I'm looking for, well, I have dx dt. I'm looking for d theta dt. I need something with an x in it. So maybe not sine. You said cosine, right? Maybe cosine. Cosine is adjacent over hypotenuse. Adjacent is x. Hypotenuse is h, right? That definitely has theta in it. It definitely has x in it, but it also has h in it. And again, if h is there, when I differentiate, I'm going to have a dh dt, and I don't know anything about dh dt. So maybe that one is no good either.
Tangent?
Tangent? Okay, what about tangent theta? Tangent theta is opposite over adjacent. The opposite side is 2, and the adjacent side is x. Ah, there we go. That equation has theta and x and just theta and x, right? No h in there. So kind of in retrospect, looking back at this now, when we were trying to connect the theta and the x together, we could have looked at sine, cosine, or tangent. Tangent brings the 2 into it, right? And since the 2 is fixed, that's a good thing, right? We don't want to bring h into it because h changes and we don't know anything about dh dt. So I'm going to use that equation there. Tangent theta is 2 over x. Look at the way I wrote that. I didn't write 2 over x because I'm already thinking I need to take the derivative, right? And 2 over x, I don't want to treat it like a quotient rule. I'd rather bring the x up and look at it as x to the -1 and then just use the power rule when I do the derivative. So there we go. Let's take the derivative. Who wants the derivative of this? Please, not all at the same time. Please don't interrupt each other like that. I want some fresh voices today. What's a derivative of tangent? We're taking derivative with respect to t on both sides.
It's secant squared f.
In this case, it would be secant squared of theta, right? Okay, so we've got secant squared theta. Good. That takes care of the derivative of tangent. Don't forget chain rule. So Shams, what else do we have there?
Then times the x. I mean the theta.
The derivative of theta, right?
Yeah.
The derivative of theta with respect to time, which is d theta dt. Right? That's your chain rule. We first had to look at, hey, we're taking the derivative of tangent of this purple blob. The derivative of tangent of the purple blob is secant squared of the purple blob. And then we say times, now we take derivative of the purple blob, which is the derivative of theta with respect to time, which is d theta dt. See, we have to have the d theta dt there, right? We have to. If we don't, then we're never going to be able to solve for it, right? Look, that's what we're trying to find. So it needs to appear. That's where it appears, right here with the chain rule on this. Good. Who wants the right side?
It would be negative 2x to the negative second.
Negative 2x to the negative 2. Good. That's your bringing the negative 1 down. You're subtracting 1 from the power. Good.
Times dx over dt.
Perfect. Times dx dt. That's continuing on that chain rule. You first bring the power down, right? Subtract 1 from the power. Then you have to go and take the derivative of what's in here. And derivative of what's in there is a derivative of x with respect to t, right? That's why it's not 1, it's dx dt. And yeah, I think we're good. Any questions on that? The chain rule is like critical, right? Y'all seeing this now? I mean, it's like absolutely critical that you understand chain rule. It makes everything else impossible to do if you don't get it. Okay, I'm now going to just take a look at this. I want to just kind of think about what I know, you know, what am I happy to see? What am I not happy to see? I'll rewrite it up here. I have secant squared theta times d theta dt equals negative, watch the way I write this, negative 2, I'm gonna write it this way, negative 2 over x squared times dx dt. So what I did is I decided to go ahead and rewrite that x to the negative 2 and drop it back down as an x squared on the bottom, because I'm done taking derivatives and it might just be easier for me to plug it in here. So in looking at this, the only thing I really kind of know right off the bat is what dx dt is, right? I know that that's negative 600. The d theta dt, I'm actually happy to see because that's what I'm solving for. But I don't know what x is, and I don't know what theta is, do I? Not right off the bat, right? I don't. So I'm going to have to go figure out, you know, what's theta and what's x. And now at this point, you can look at the instant in time. You're allowed to go over to this picture now. We know that this side was x, and we know that this is theta. Can you get me x? How can you get me x?
Pythagorean theorem.
Pythagorean, I can get x off Pythagorean. Let's do that. X squared plus 2 squared must be 6 squared. So x squared plus 4 must equal 36. So x squared must be 32. So x must be plus or minus root 32, but I'm only going to look at the positive answer because x is a distance here. So it wouldn't really make sense to be a negative distance. So I know what x is. How are you going to get theta? How are you going to get theta? Well, you know this side's 2 and this side's 6, right? You know the opposite side is 2 and the hypotenuse is 6. Yes, at this instant in time. Well, wasn't that the sine function? Don't we know that sine of that angle theta must be opposite over hypotenuse, 2 over 6? So sine of theta is 1/3. Any questions there? I still don't know what theta is, but do you agree that sine of theta is 1/3? Yeah. Now, how can you get theta from this? This is pre-cal.
Do you use the inverse of sine?
Use the inverse sine function. So you're probably going to need a calculator. So if we take the inverse sine, very good, on the left side, and we do inverse sine on the right side, Then the left side becomes theta and the right side, I need my calculator. Now I'm gonna make sure my calculator is in degree mode. That way, when I give you my answer, it's gonna be in degrees. So on my calculator, I'm gonna do the inverse sine of 1/3. And I get approximately 19.47 degrees. You all good? So now I can come back to this and I can start plugging things in. Now, before I actually plug in the theta here, I want to make sure y'all all understand what secant squared theta really means. So I'm gonna do that over here on the side. Secant squared theta really means secant theta squared, right? That's really what that notation means. And secant, by definition from pre-cal, is the reciprocal of cosine. So secant theta is 1 over cosine theta. Now, the reason I'm doing that is because our theta is 19.47 degrees. I'm going to plug 19.47 into this and figure out what all this is. Because my calculator doesn't have a secant key on it. So I only have a sine and cosine key. So that's why I'm switching that secant over to 1 over cosine. Okay, so this piece here is going to now turn into 1 over cosine of 19.47 degrees, all of that squared, times d theta dt, which is what we're looking for, equals -2 over x, which we said was the square root of 32, but then squared, and then times dx dt, which is -600. Y'all see that's me just plugging all the things in? Let's go ahead and take care of this left side. I'm gonna do this all on my calculator and give you just the final result from this, and hopefully you'll be able to do it on your own. If you can't get this same answer I get on your calculator, you might want to talk to me at the end of class and just be like, hey, I wasn't getting what you were getting. So on my calculator, I just did 1 divided by cosine of 19.47. I'm in degree mode on my calculator, and then I'm squaring that answer. So I get 1.12, I'm going to round it 3 decimal places, 1.125 times d theta dt equals, and then over here, I'm going to multiply those two together. That gives me positive 1200 over root 32 squared is just 32. On the right-hand side, I'm going to go ahead and do 1200 divided by 32 and get 37.5. And then finally, I will divide both sides by 1.125. And I'll get my result here. D theta dt equals 37.5 divided by 1.125. It's approximately 33.33. It looks like repeating almost, but I'll just say it's approximately 33.3. Questions on any of that? We need the units. Okay, now please pay attention. Be very careful on this. Theta and t are units, right? T is time. That's the easy part. Time here will be measured in what? What is things measured in here time-wise?
Hours?
Hours, because the plane was flying at 600 miles per hour. So I know this is going to be 33.33 something per hour. And this is the part that confuses most students. The angle theta. How are we measuring the angle theta? I know you're going to want to say degrees because we were in degree mode on our calculator. However, This is whenever you do a related rate problem like this and you solve for d theta dt, your answer will always be in radians per whatever unit time. So this would be radians, I'll just put rad per hour. 33.33 radians per hour. Now, if you wanted to know that as a degrees per hour, you would have to convert 33.33 radians to degrees. Do y'all remember how to convert from radians to degrees? You multiply it by 180 and divide by pi. That's how you would convert from radians to degrees. So if you wanted to know what this was in degrees per hour, you go 33.33 times 180, divide that by pi, and you get approximately 1909.7 degrees. 1909.7 degrees per hour, or 33.33 radians per hour. Okay, question, yes.
Why, even though we did all the work in degrees, why are we converting it to radians? Is it because it's distance?
Okay. When we did degrees, right? When we did degrees right here, right? We plugged in degrees right here. Cosine of this degree is a number, right? That's just a number. We're no longer in degrees anymore, right? We're no longer in degrees. So we only use the degrees when we plugged into cosine. Once we did that, it just gave us a numerical answer. So this number is no longer in degrees. That's not a degree measurement. And this is not a degree measurement either. So all that's left is the d theta dt. This is a measurement of your change in angle with respect to time. And the default measurement for all angles is radians, okay? All angles are measured in radians unless you want to convert it to degrees. Then we convert. You may remember in pre-cal, hopefully your instructor told you that basically radians is what we call like a unitless measure. It's the default. Everything's in radians unless we want to convert to degrees. Now, when we're learning degrees and stuff in radians and pre-cal, we always like to talk degrees because that's what most people are familiar with from like lower levels of math, right? And 90 degrees, 180 degrees, 360 degrees, but really the default is radians. I don't know if that answers your question, Ash.
It does. It does. It makes
Okay.
sense that it no longer was a degree once we took the cosine.
Once you took cosine of it, exactly. And you
That
know
makes
what, up
sense.
here, Ash, up here, we could have solved this up here and we could have got this answer in degree, I mean, in radians on our calculator, right?
Yeah.
And if we would have done that, then we would have had everything in radians. And then again, they would have gone away because we would have done cosine of some radian on our calculator in radian mode, and then we just get a number. So then the question again becomes, what's the default for measuring angles? And it's radians.
So can we say now that on the solution portion, you did convert the radians to degrees, what if we wrote 1909.7 degrees per hour? Would that be wrong?
That'd be correct, but you would have to put the degree symbol on this number,
Okay. That's
okay?
fair. Thank you.
Okay, so that problem is very different than what we did last time, right? With the one we did last time, same airplane, we wound up, did we not finish it? We didn't finish it, did we? I thought we finished it. But you use Pythagorean here, right? To set up your equation, you use Pythagorean. Do y'all want me to finish this one or do you want to just move on? Okay, thumbs up if you want me to finish it. Thumbs down if you want me to move on. I think I have the same number. Okay, I think I have, it's close. Now we got a lot of non-voters there. Let's do it this way since no one wants to play nice. Let's do this. Yes, let's do it. No, let's move on. Ooh, it's close. Back and forth. This is like that dot races at the Spurs game. All right, that's everyone. Boy, y'all voted fast today. What's going on? One vote. It came down to one vote, so we're not doing it. But I'll do it at the end of class if we have time. I can't stay after 2:40, but I'll be back in my office hours at 4. So I'll try if I have time to finish it up. I really want to get these other problems done though.
Sir, I have a question. Where is
Yes.
that? Where can we find that sheet that you're working on?
In Canvas under files,
Okay.
right? It's there, everyone, right? Isn't it? Yeah, it's in Canvas under files, called the related rate worksheet.
Okay.
All right, so back to today. All right. I'll give you a minute to read. All right, so can you visualize what's happening here? Let's try and draw a picture. I have a street light that's a pole that has a light on top of it that's 20 feet tall. That's not going to change, right? So in my picture, in both situations, I have the ground and then I have a 20-foot pole over here with a light on top of it. Check out my light. Look at that. Isn't that awesome? Okay. And then over here, we got the same situation, right? It's light up here. And we know that this is 20 feet, not changing. All right, then I have a man that is 6 feet tall that is walking away from the pole at 7 feet per second, right? 7 feet per second. That's pretty fast, actually. Might be a light jog. Okay, so I need a 6-foot man in my picture. So here's my 6-foot man. I told y'all last time, don't be intimidated by my artistic abilities here, all right? I know that that is an impressive man. I'm gonna move him a little bit to the right. Remember, in this general picture, it doesn't matter where he is. Okay? I'm not gonna go to the instant yet. Let's just continue the general picture. What are we interested in? It's got a man, he's walking. Let me see, let me put a little arrow down here just to let everyone remember that this guy is moving at 7 feet per second to the right, right? Going away from the pole. It's just to remind me that he's in motion to the right. How fast is his shadow moving along the ground? You know what, this should say how fast is the tip of his shadow moving across the ground? How fast is the tip of his shadow? Tip of shadow moving along the ground. So do y'all see where his shadow would be? If this light is shining, right, then his shadow would look like this on the ground. There would be wherever the light would come and hit his head, that's where his shadow would be cast on the ground. It would be like here's his shadow on the ground, right? Kind of. And so the tip of the shadow would be right there where his head is, his shadow of his head. I want to know how fast that's moving along the ground relative to the pole, right? It says, how fast is the shadow moving along the ground relative to the pole when he's 12 feet from the pole? So I want to know how fast this dot is moving to the right. If he's moving at 7 feet per second, how fast is his shadow, tip of his shadow moving? So why don't we call that, what do y'all want to call that? Distance from the pole to the tip of his shadow. It's changing, right? We can call it a variable. What do you want, Bella?
S.
S for shadow? Is that what you said? Yes? Okay. I'm gonna use S. I like it. So would you all agree we could right now just write we want ds dt? Because we want to know how fast that thing's moving. At what moment do we want it? When he is 12 feet from the pole. So that means when this guy is standing here, well, he's moving. When he's 12 feet from the pole, is that instant in time picture, right? And then we've got the shadow coming down here like this. There's his shadow on the ground. Help me out. We want to know how fast this shadow's moving, right? S is the distance from his shadow to the pole. We want to know how fast that thing's moving, right? Does someone want to help me with what we're given and what this at, like at what moment?
12 feet.
I'm sorry, Ash?
At 12 feet.
At what's 12 feet? Sorry, I shouldn't have put equals here. At what is 12 feet? I agree with you that this should be at something equals 12 feet. Something equals 12 feet, but what?
Oh, like you want to assign a variable to it?
Okay, good. So it's not S. Does everyone understand S is not 12? Because S is the distance from the pole to the tip of the shadow. When he is 12 feet from the pole, we're talking about a different distance. It's the distance from here to the man, right? That distance is 12 feet. Let me get rid of that, yeah? Do you see how that's different than S?
Mhm.
Okay, so we need to label that a variable because it's changing as well, right? So what do you want to label that? How about M for man? Is that okay? We call it X, but let's go M for man. So that means I want to know how fast S is changing when the man is 12 feet away from the pole. Y'all getting this or no? What are we given? We're given the rate at which something's changing. What?
DM.
DM, the man, right? I know how fast the man's moving. The man is moving with respect to time at 7 feet per second. And is it positive or negative?
Positive.
Positive. M's growing, right? M's getting bigger, so it's positive. Hey, I think we have everything, don't we? We've got a picture of the instant in time when he's 12 feet from the pole. I've got the general picture. S is changing, M is changing, 20 is 20, he's 6 feet tall. Let's not forget he's 6 feet tall. And I know dmdt, I want dsdt, and I want it at the exact moment that M is 12. Which means you need to come up with some equation now that's going to pull these variables together, M and S. And you can only look at that general picture right there. So I'm going to show you that general picture here now. Here's that general picture, right? I'm going to zoom in on it. And I'm going to clean this up a little bit, okay? I'm going to make this look a little nicer because I think if I do this, it might help you. Okay, we have the pole that's 20 feet. So this is 20. We have the man that's 6 foot. I'm going to draw him as just a little stick now, okay? Then we have the shadow that's being cast off the top of his head to the ground, like that. We know the distance from here all the way, we're calling S. And the distance from here to here, we are calling M. Or that's the same picture, just without all the beautiful detail, right? It's good detail, right? Help me out here. I mean, you can see the decades of experience I have. All right, equation. Got to put the M and S together now in the equation. Anything out there that you can think of that's correct, it has to be right. But, and I'll give you a hint. We haven't done anything like this yet. So it's not Pythagorean, it's not sine, cosine, tangent, it's none of that because we're not even talking about an angle.
I
So
think we should like find what S is and then subtract M. I don't know.
so what do you mean find what S is?
I don't know. I just thought like we should find like an equation for S and then M should be subtracted so we can find the shadow. I don't know. Maybe I'm wrong.
Okay, yeah, no, I thought you meant, what I thought you were saying is since we know that M is 12, let's go find S. That we might have to do. But see, that would be looking, oh, where'd it go? That would be looking at this picture. And we're not allowed to look here when we're trying to come up with the equation. We must look at the general picture. We have to let everything still be in motion when we do the equation. So I don't want to fix anything yet. But, well, I don't know. I mean, you're not wrong. Some of the things you said are correct, but it's, I'm going to see if anyone else can see it.
So could I make a rectangle in the middle of the triangle, of the big triangle, to find the hypotenuse of the distance between the top of the man's head and the top of the pole, and then from there figure out something?
Okay, so let me state what I believe you're saying, or let me draw what I think you're saying. I think you're saying you want to make a triangle like this here, and then somehow just figure out what this distance is. And then from there, I don't,
Oh,
you're not
we
quite
have-
sure, but
Yeah,
you
I don't
can
know.
maybe
We
mess
have
with
an
it, right?
angle, no? It wouldn't be
We
a
don't have an
relationship.
angle.
No?
We don't have an angle because remember, this thing is in motion, right? So the angle's constantly changing.
But
Right?
it's in the 90 degree? Oh, no.
Yeah, oh yeah, that's 90 for sure. Yeah, we know this is 90, as long as that pole is vertical, which
we
we're
have-
assuming.
Oh, no, we don't have it. But yeah.
So look, what you said about the rectangle, Robert and Bella, I mean, it's not wrong, okay, what y'all are thinking, because it could lead us there, all right? It could lead us there. But in any others before, I'm just gonna show you because we could sit here all day, perhaps.
Don't we have a right triangle already though with the man?
Yeah, you do. Right there, you have a right triangle, yep.
So I guess it would be the bottom. We would have basically the bottom of the opposite and the adjacent. So we could find the distance between the top of the man to the shadow.
Top of the man to the shadow, like this distance.
Mhm.
In order to find this distance from here to here, you would have to know this distance.
Oh, right, because we would need, yeah.
Well, what would this distance be?
S minus N. Or
S minus M. S minus M. Okay, everyone, let's make sure you all understand that. Imagine that this, just for the sake of making you understand, let's say S was 30 and M was 10. What would this be? If this was 30 and that was 10, that would have to be
20.
20, right? If this was 30 and that was 18, that would have to be 12, right? So whatever this is, take away this, and that's what the remaining piece would be. So I could do this. This is not wrong. This is not wrong to realize, but this distance from here to here is S take away M. Do y'all agree with that? I'm not saying it's going to get us anywhere. I'm just saying, do y'all agree that that's true? Whatever S is, take away M, and that'll be that remaining piece. If you don't believe it, add these two together. What's M plus S minus M? What's M plus S minus M? S, right? So those two added together should be S. All right. Any last, James, that's going to help us, but does that, anyone have any last thoughts before I show you?
Oh, yes. Well, kind of.
Okay.
Sorry. Are they the same? Like, are they the same triangle, but
Almost.
on a scale? Yeah. So like what we
okay.
get for one.
Ash, you got it. Good. So what we're looking at here are actually what are called similar triangles. All right. So this is going to take you back to some place in your past that you may or may not remember. So let me remind you what two similar triangles are. All right. So I'm going to break from that up there. Similar triangles. Oh my gosh, triangles can't. What are similar triangles? So let's say I draw a triangle. Okay. Doesn't matter what the triangle looks like. Just draw me a triangle. Okay. Let's call this angle A, angle B, angle C. Let's call this side little a, little b, little c. Notice that the angles we use capital letters and the sides we use lowercase letters, and the sides are always opposite of the angle. Okay. Then let's say we have another triangle that's not necessarily the same size. Maybe it's a little bit bigger, but it still has capital A, capital B, and capital C here. In other words, the angles match. Okay, so like if this is 20 degrees, that's 20 degrees. If this is 80 degrees, that's 80 degrees, right? All the angles inside match. Then this side over here, I'm going to call it C tilde. That's just because it's not necessarily the same C as this one. Call this A tilde, and we'll call this B tilde. So if you ever have two triangles that have the same angles, but they're different sizes, those are called similar triangles. And what's important about similar triangles is this: the ratio of any two sides are congruent. Okay, what do I mean? What I mean is this: if you take this side C and divide by C tilde, that will be equal to you taking the A and dividing by A tilde. But it's also equal to if you were to have taken the B and divided by B tilde. The ratio of corresponding sides are congruent. The ratio of corresponding sides, are congruent. I'll just say equal. The ratio of corresponding sides are equal. That look at all familiar to you at all? Similar triangles? Maybe, maybe not. What's really kind of interesting about this is that there's another way it doesn't have to be C over C tilde, A over A tilde, B over B tilde. It could also be this. I could do C over B must be congruent or equal to C tilde over B tilde. And you could do that with any sort of matching pair you want. If you wanted to do these two together, you could say A over C must be equal to these two, A tilde over C A tilde over C tilde. Doesn't matter how you do, just gotta match corresponding sides.
There, the D wasn't supposed to be a B, or is that other side?
You know what? Wait, which one?
In the top,
Oh,
yeah, that one.
what? That was a B. Yeah, thank you.
Okay, okay.
I wrote a D. I probably said B and wrote D. Sorry about that. C over B would be equal to C tilde over B tilde. All right, so why is that? How is that going to help us? Well, we go up here and now what we do is we redraw this. And what I have is a big triangle. Let me do it this way. I have a big triangle that looks like this. Come on, man. Jeez. A big right triangle like this, where this side is 20 and this side is, this side is S. That is this triangle right here, right? I have that triangle. And then I have a smaller triangle where this is 6 and this is S minus M. That's what James had brought up earlier, right? That this little piece right here is S minus M. It's also a right triangle. Now, do they have the other, do all the angles correspond? So when you look at these angles, look at this angle right here in the big triangle, that angle right there, whatever that angle is, do you all agree that that's the same as this angle? Yes? So this angle must be the same as this angle. And they both have the same 90-degree angle, right? And that forces the other angle to be the same. You could also have just said, look, look, obviously this angle is the same in both, right? It's part of the big triangle and the small triangle. So this angle is the same, the 90 degrees the same. And so do y'all see that these have the same angles inside? And so they're similar triangles. And so since they're similar triangles, I can set up a ratio of any two sides with any other two corresponding sides, any way I see fit. So here's how I'm going to do it. I'm going to do these two. I'm going to say 20 over S must be equal to, how would I do it over here? How would I write the next one?
6 over S minus M.
Yeah, 6 over S minus M. I would not do it the other way around. I would not, if I do 20 over S, I must do the 6 over the S minus M. I can't do 20 over S and then say S minus M over 6. Has to be corresponding. Yeah? Is that an equation that has the variable S and M in it? There you go. We have an equation with S and M in it. So we just need to take the derivative of that with respect to time. However, I don't want to because that looks pretty nasty. So I'm going to just do a little algebra first. Okay, I'm going to do a little algebra first. I'm going to do like a cross multiply, multiply that 20 times the S minus M, and then equals the 6 times the S. I'm just kind of cross multiplying. This gives me 20S minus 20M equals 6S. And that gives me 14S equals 20M. I just decided to move my S's to one side and my M's to the other. I didn't have to do that, but I figured I would, because that's a pretty nice looking equation, right? So even though this looked bad here, this is actually pretty nice. I'm not going to be unhappy about differentiating that. Questions before I get back to our worksheet? 14S equals 20M. 14S equals 20M. I was trying to connect S and M together with an equation. I realized I had similar triangles, and so I created the equation. Differentiation is going to be beautiful. 14 comes for the ride. The derivative of S with respect to time is ds dt. 20 comes for the ride. The derivative of M with respect to t is dm dt. And that's it. I mean, this is a clean derivative, right? There's no like chain rule involved, really. 14 comes for the ride, take derivative of s with respect to t. 20 comes for the ride, take derivative of m with respect to t. And now I look, am I happy about this? 14 ds dt equals 20 dm dt. So dm dt, I have ds dt, whoa, ds dt is what I'm looking for. So I have everything I need, don't I? I have everything I need. Something curious here. Something curiously different in this problem than the ones we've done before. Does anyone notice it? What doesn't appear to be needed for me to get the answer?
The hypotenuse.
The 12. Or,
The 12, right? Remember this was at m equals 12. Do you see an m anywhere in here? No, just a dm dt, right? That means that I'm never going to use that 12 in the answer to get my answer. I'll get back to that. Let's just get the answer. So I'm going to replace, I'm going to just replace the dm dt with 7, right? And then I'll divide both sides by 14. And when I divide by 14, I think you get 10, right? Because you get 140 on the right-hand side divided by 14, you get 10. 10 what? S. S was the distance on the ground. How are we measuring distance here? Feet, right? Wasn't it feet? Per time, what was our time measurement here?
second.
Seconds, 10 feet per second. Okay. Questions on any of this? I mean, I want to explain what this means over here, because this is actually this is pretty profound what's going on in this geometric problem. But there's no questions leading up to this. Everyone understands what I did? So now wrapping our heads around all of what's happening here is we've got this man, he's walking away from a pole at 7 feet per second. The tip of his shadow is moving along the ground, how fast? At 10 feet per second, right? When though? When is his shadow moving at 10 feet per second? When he's 12 foot from the pole? Well, the 12 foot doesn't matter, which means that this would be the answer for him at any position, which means that his shadow is moving at a constant rate of 10 feet per second. That
Yeah,
might
because he's
seem
not getting
counterintuitive. Bellum, go ahead, I'm sorry.
Yeah, I was just reasoning because he's not getting taller at all. Like it's pretty much
He's
the
not.
same.
He's not getting taller, but I personally think that this is counterintuitive, because let me bring up the picture, the animation of it. Slow it down a little bit. So as this man walks away from the pole, right, he's moving at a constant rate. But we know that the further he gets away, doesn't his shadow get longer? Think about this. If I actually show you the shadow on the ground, here's his shadow. As I start to move, watch how his shadow grows, right? And the further he gets, the longer that shadow gets, right? So in your mind, you might think, okay, as he walks out, the further he goes, the faster the tip of his shadow moves away, because it's got to get longer. Does that kind of make sense? That's maybe what you would logically think is happening? That's not what's happening though. His shadow is moving along the ground at 10 feet per second all the time. And so, I don't know, I mean, Like, let's say we didn't have the calculus. Let's say we didn't have the related rates. And you and I were having this discussion about the shadow and whether or not that shadow is speeding up or slowing down. We could argue about it all day long. And you could make your argument, no, I think it's speeding up. And I could make my argument, no, I think it's staying the same speed. We could argue all day and never settle anything. We need math to settle things like this. Because sometimes in the real world, things do not behave the way we think they're going to behave. And so we don't want there to be any sort of like guess, right? Especially if you're building a bridge or an airplane. Okay. Had this answer, had this derivative right here, had an m in it, then yeah, absolutely. How far away he was would matter, right? If I plug in a 12, it's going to change the answer. If I plug in 20, it's going to change the answer. This is telling me that his distance from the pole is irrelevant. That's what it's telling me. Okay. I feel like I skipped a problem. No? No. Okay. Here we go. I'm gonna let you read that one. Should I give you a little bit of time to try and like draw things and see how you do? I'll give you, let's say, I'll give you 5 minutes, just see how much you can come up with in 5 minutes. In case you don't know what I mean by a conical cup, think about if you've ever seen those little paper cups that look like this. That's a conical cup. I'm playing a little animation to show you what's going on here. If you're pouring water into a cup that's in that shape of a cone, and you're pouring it in at a constant rate, then in the beginning, the level of the water is going to come up very quickly because it's very small volume down there. But the further up you come, the slower the water level is going to rise because the cone just naturally spreads out. So we're interested in the rate at which the water level is rising at a specific instant. We'll go another minute here. I guess another way you can look at it is if we reverse the direction and thought about it going like water coming out. If it was being drained out at a constant rate, then initially it would be going down slow, right? But the closer it gets to the bottom, the more it speeds up. You know, kind of see it speeding up there. It's going to get real fast here at the end. It's gone, right? So we're kind of doing that, but in the opposite direction. Oh, no, it's going back and forth. Oops. I have a lot of computer science majors in here, right? Or at least a handful. So this is the code that I had to write to make that animation happen. It's kind of C+ based code, but there's a bunch of built-in functions. So it's not truly like C+, but it has a lot of the same syntax that C+ has. That's Wolfram Mathematica is the program I use to do all my notes in. And Wolfram Mathematica is a C+ based program. And yeah, so anyway. You ready to talk about this? Let's do it. And draw a picture. And draw a cone first. I'm gonna draw my general picture. So I've got a cone. Is there anything to know about this cone? Conical cup is 4 inches tall and 6 inches wide. So I guess I didn't draw it very good, but we're gonna say it's 4 inches tall and 6 inches wide. Is that going to change? The cup itself isn't changing, right? That's not what's changing. What's changing is the water within it, right? So inside of that cone, we have another cone, which is the water, right? Now let me just let me draw this again over here. I know this is 4. I know this is 6. Excuse me. And then at the instant we're talking about how fast is the water level rising when the water is 1 inch from the top of the cup. So the water level is pretty high. It's way up here. And I know that the distance from there to there is 1 inch. Is that a pretty good picture so far of what's going on? What am I interested in? D something, D something. What am I given? D something, D something. Again, I told y'all last time, and I'm trying to stress this right now. Like when you do these, there's not like one thing you do before the other. You just kind of are trying to put all the information together to get to your equation so that you can differentiate. So does anyone want to interject some information here for me?
Is what given d height over dt
The height,
or no?
let's see, is that what you're given?
Yeah.
Water is being poured into a cup at a constant rate of 2. Okay, so here's the word rate, right? Derivative. That's a derivative of something. 2 cubic.
Oh, so it's volume.
Is,
Yeah.
yeah, it's volume.
Yeah.
They're giving you the rate at which the volume is changing. I know that because cubic inches is a measurement of volume. Cubic inches a second is volume over time. So do y'all understand that? I'm given dV dt. dV dt is 2 pi cubic inches a second.
Then B will be 3.
And what?
B will be 3
Did you say
in
B?
given. Yeah, the volume of the liter cone.
So
Well,
it says
the- not
how
H.
fast is
It's
Or what?
H, right?
H?
Because we're given the height of the liter cone, no?
Okay, we're
which will
given
be
the
3.
height. We're given the height of the water at the moment in time, right? How high is the water at the moment in time?
3.
You said 3, right? Does everyone follow that? 1 inch from the top means the height of the water is 3. Well, height, I better label height on here, right? So I'm going to label the distance from here to here H. It's changing, right? It's changing in this picture. In this picture, that height is 3. Y'all understand? On the left picture, it's fixed at 3. In the right picture, the water level is changing. So Bellum is saying, hey, we want to know, what do we want to know? We want to know how fast is the water level rising? Isn't that H? I want to know how fast H is changing. The water level is H.
Mhm.
So I want to know how fast H is changing with respect to time at exactly the moment that the H is 3. I don't know about you, but I think we have everything in terms of what we're given and what we want. I'm sorry I'm eating. I'm just so hungry right now. What next?
The equation.
Equation. What variables am I trying to connect?
H and V.
H and V. Now, we're trying to connect the height of the water to the volume of the water, right? The cone is only giving me the general shape of everything, right? But everything we're talking about is the water right now. So I need a formula that somehow connects the volume of the water to the height of the water. Well, it's a cone, right? The water is a cone. So I'm going to go to my formulas and I'm going to hope there's a formula for volume of a cone. Ah, there it is. Look at that. Look at that. In my Cal 2 class yesterday, we proved this formula. We actually showed where this formula comes from. All right, so let me squeeze that in right here, maybe. See where it wants to put it. No, it wants to put it way down there for me. It's weird. There we go. Oh, come on. Get up there. Get in there. Doesn't like to be pushed into this document. Okay, so that's kind of like what I'm going to use now. All right. The volume is 1/3. Volume is 1/3 pi times the radius squared times the height. Crap. I've got V, right? I've got H in my picture, right? H is the height. Obviously, it's that cone flipped over. That's okay. Then we're just doing it flipped over. All right. What about the radius? I don't see. There's an R in my formula, right? In the formula for volume, there's an R, but I don't have any information on R, do I? No information on R.
We know the
just-
width of the
Uh-huh.
cone,
We do know the width of the what?
of the top of it,
Of the top of what?
The cone.
the cone.
The cone, I agree. But does that tell us the width of the water? Because remember, the water is moving, right?
Can we use
So-
the same relationship we used in the past problem? Because it'd be similar.
There's
Like
something
cones?
similar. Yeah, there's something similar. So before I get to that, I just want to make sure everyone understands, we cannot fix the radius to be 3 here. Okay, you cannot tell me, you cannot, when we're looking at this water in here in yellow, is it beer? Is it beer or is it water? I don't know what it is. That looks more like beer. I don't know, it's pretty yellow beer though. All right, so there we go. Is that the distance from here to here? That's our radius, right? We'll call that R. That's not 6 all the, I mean, it's not 6. That's not 3 all the time, right? I mean, it's only 3 when it gets to the top. As the water comes up, that radius is changing, right? So I can't fix that radius to be anything. Unfortunately for us, we can't. So to kind of just take a step back, the problem we're running into is we have a formula, right? We're happy to see the V, we're happy to see the H, right? What we're unhappy about is the fact that there's an R in here, because I don't know anything about R. But Bellum just mentioned that maybe we can do something like the previous problem. So can you elaborate on that? What do you mean?
Yeah, so we have 6 and 4, which will be equal, like 4 to 3, and then we can find the relationship between 6 and the new radio. Well, 3 and the new radio.
Okay, I think you got it. Let's see if I can help everyone else get it. There's my water, my beer, whatever. It's almost Fiesta, right? Fiesta's next week? Is Fiesta next week? All right, that'll be beer then. All right, so I want you to imagine that we came in through here and we cut this cone in half. All right, but the beer doesn't spill out. We're doing some magical thing where we're taking a cross section. We're coming in through with a knife and we're just gonna cut this thing right down the middle. Okay, and we're going to open it up and we're going to look at it from the side, a cross section. Here's what you would see. Your cone would now look like this, right? Because we're looking at it directly from the side. And then you'd have your water level in here, or your beer level, right? If you draw right down the center like this, you have now created 2 right triangles here on the right hand side. Just ignore the left for now. In other words, you have this. We know the distance from here to here is what? Never changing, right? That's 4. We know the distance from here to here is the top radius of the cup, which is 3. We know that the distance from here to here is R because, well, that does change as the water comes up. And we know the distance from here to here is H, and that does change. But now we've got our similar triangles. If you're having trouble seeing the similar triangles, then I'll draw them separately. We have one big triangle that's 3 here and 4 here. Okay. And then we have the smaller triangle which is R here and H here. Do y'all agree that they're similar? They both have this same common angle. This bottom corner right here is the same for both the small triangle and the big triangle. And they both have a right angle here, which means that this angle has to be the same. Have I updated y'all on my weight loss? Right, have I told y'all about that? What was the goal? I was trying to get what? 12 pounds in 12 weeks? Was that the goal? Do I remember?
I
You
don't
didn't-
think you have told us
Yeah,
about
you
your
didn't
goal.
mention that.
I haven't told y'all about it? Really?
No.
I haven't told y'all
Yeah.
about it?
No. I'd
Well,
like
I
to
need
hear
to
more
tell y'all
about
because
it.
I offered all my other classes this. 6 weeks ago, I offered my other classes that I was going to start getting healthy and that if I could lose 12 pounds in 12 weeks, I'd give everyone 5 points on their final exam. Okay. And that was 6 weeks ago. Today, 20 pounds, I'm 20 pounds I've lost. So I hit that goal like a long time ago. So I thought I had told y'all. So y'all, everyone's going to get a 5-point bonus on that. Unless I somehow put on 8 pounds in the next 6 weeks. That's not going to happen. So I'm hungry because I'm just like, I'm working out so much and I have to eat. Anyway, okay. I used to be very active, do triathlons and things like that. And I had an injured my knee right before COVID and it was bad. So I'm finally able to work out again. So it's good.
Oh, congrats. Thank you.
That's why I'm so hungry though. I'm just like, I want to eat everything. Okay, so we've got our similar triangles. So I can set up any ratio I want. Who have I not heard from? Let me see. I'm going to pick on somebody who doesn't have their video on. Chloe, are you there?
Yes.
Okay, are you understanding? Do you understand the similar triangles idea that you can set up a ratio?
Yes, it's starting. to come
Okay,
back.
so give me a ratio. Give me any ratio that you want to use off of those similar triangles.
So we can do 3R and 4H.
3 what?
3R and then 4H.
Just 3 times R? Is that what you
Oh,
want?
divided by R.
Okay,
3 over R,
R,
and 4 over H.
4 over H. Okay, everyone agree we can do that? Yeah, I agree. We can do that. And is it all right if I just cross multiply that? Because I hate fractions. You hate fractions. We all hate fractions. Let's just do that. 3H equals 4R. Now, be careful, everyone. This is not the equation we're going to use for the problem. This is not the equation. All this is doing is giving me a new relationship between R and H. Remember, the issue we were having was that in the problem we're trying to find, we didn't like there being an R in here, right? We were like, no, we don't want an R. We're fine with an H, we're fine with a V, but no R's in here. But then we used the similar triangles and we realized, guess what? There's a relationship between the R and the H. So if I take this and divide both sides by 4, I have an equation for R that has H in it. So I can go back to that volume formula now, and I can replace R with 3/4 H. And then that equation won't have R's in it anymore. It'll have just H's. Okay, so let's go do that. So volume equals 1/3 pi. And then I have R, which we just said was 3. I really don't like, I'm having to cram that in here. Let me do this down here. We had volume was 1/3 pi R squared H. And I just replaced the R with 3/4 H, then squared times H.
I have a question.
Yes.
Why we don't use the 3 that we already know?
The 3. Okay,
Yeah.
so so why don't we use this H equals 3?
Yeah.
Okay, so the reason we don't is because if you're letting H be 3, then everything is fixed, right? Now your water level is stopped moving. This goes back, I don't know, if you were in the class last time, when I was talking about if I'm running, right?
Yeah.
And you take a picture of me in the middle of my running, you can say, hey, how fast were you moving when you took that picture? And it makes sense to say, oh, I was going, 7 miles an hour, whatever. But if I just like stand there and I stop moving and then ask you, hey, how fast am I going? And I'm not moving anymore, then you can't tell me how fast I'm moving. I'm not moving. So if you fix the h at 3,
Yeah.
you've then stopped it from moving and then asked me how fast is it moving. We can't fix the h until after we say how fast are you moving.
Okay.
And what I mean by how fast are you moving is you have to take the derivative. So the derivative has to come before you take, sorry, the derivative has to come before you fix anything.
Okay. Yeah.
Great question. Great question, because that's fundamental here, is that you cannot actually plug in the moment in time until after the differentiation has occurred. Once the differentiation has occurred, then yes, plug anything you want into it. Okay, I think I'm ready to clean this up. I'm not ready for a derivative. Volume equals 1/3 pi. I'm going to square this. So this gives me 9/16 h squared. And then I still have to multiply by h. So when I square a fraction, I square top and bottom. When I square the h, I just square the h. And then let's put this all together. Volume equals, let's see, that 9 and the 3 down there, that reduces out. I'll get a 3 on top. So 3 pi over 16 was still there, and then h cubed. There's the volume of the beer in terms of the height of the beer. You give me the height of the beer, I give you the volume of the beer for this particular cone. If you change the cone on me, different shaped cone, it's going to be a different formula. But for this one, this is the relationship. So now I differentiate dv dt, that's the derivative of the left side. And then on the right side, 3 pi over 16 is a constant. And I just have to take derivative of h cubed, which is 3 h squared dh dt. Bring the 3 down, subtract 1 from the power, chain rule, take derivative of the h with respect to time, dh dt.
I have another weird question.
Yep.
Okay. So when it's like a constant, you don't use like quotient rule, chain rule, and all that?
When what's a constant?
Like the 3 pi 16, when that's a constant, you don't use like the chain rule
Oh,
or
yeah.
the quotient rule? Or
Yeah, no, this is a constant, right? 3
Yeah.
pi over 16 is just a number. And if we
Okay.
ever have a number in front of some function and we take the derivative, the number comes for the ride, and then we just take the derivative of the function. So yeah, you don't want to start doing quotient rule and stuff on this because there's no variables in here, right? Pi is a number, 3 is a number, 16 is a number. All that together is just a number. So just
Yeah.
bring it along.
Okay. I got confused on the homework like that. Sorry.
No, these are the questions I need. I think we're good though, right? I mean, as far as this, like everything is great here. dv dt I have, right? 2 pi. H, I'm now allowed to fix it, right? Now I can fix the h at 3. And then dh dt, well, that's what I'm looking for. So it's just all, it's all smiles and high fives at this point. So 2 pi here, 3 pi over 16 here, times 3 times h squared. dh dt is what I'm looking for. Yeah, this is going to clean up here. Let's see here. 9. So square the 3, you get 9 times 3 times 3, it's 9, 81. So I'm getting 81 pi over 16 dh dt. Let me divide both sides by pi because that'll just kill it off. And then I will multiply both sides by 16 and divide both sides by 81. Does that reduce? I don't think it does. No, that doesn't reduce, I don't believe. So 32 over 81. What's my unit here? H and T, right? So height measured in this problem measured in inches, right?
Inches per second.
Per second. And I'm going to just get that as a decimal just to kind of talk about it. 32 divided by 81 is about 0.395 inches per second. So we've got this cone, 4 inches tall, 6 inches wide at the top. We're pouring beer into it at 2 pi cubic inches per second. The beer is coming up the cup. Right at the moment that the beer is 1 inch from the top of the cup, it is rising. It is coming up at a rate of 0.395 inches per second. That's the speed at which the water is coming up. So if it was like a flood, right? What we're measuring is how fast the flood level is rising at that instant. Which might be useful if this was more like a dam, right? A dam that's holding back water and you've got a flood and water's coming up and you're trying to calculate the rate at which it's coming up and whether or not you're draining out enough fast enough. And what would be more complicated with a problem like that is you would have to know the shape of the reservoir, right? If you have a dam in front of a lake, you would have to know a general shape of the reservoir. And then your volume formula over here, 1/3 pi r squared h, would not be as simple as that. It'd be something more complicated. But that's not the problem we give you when you're first learning related rates, right? It's got to be something you can do. All right, so starting to, I guess, really see some of the flavor of this. This problem was another similar triangle problem. So you had this volume formula, and within that you had this cutting it in half, opening it up. If you're sitting there going like, you know, would I have ever thought to do that myself, right? No, you probably wouldn't have. Like just thought, oh, I'm gonna just cut it open, look at it, you know. But now that you've seen it, you can kind of get a feel that these are the types of things we have to do in order to solve problems like this. So when I was giving you my notes in the very beginning of this, when we were talking about the introduction to related rates, and I was trying to like lay out the steps, you know, where was it? Here we go. You know, when I was in the very beginning, very first note, I put here, as you will see, there is an expectation here for you to know some geometry, trigonometry, basic formulas for areas, volumes, etc. Don't hesitate to Google a formula if you don't know it right offhand. So what I was trying to say there is that with the related rate problem, there's nothing that's off limits. Like it can turn out to be a similar triangle. It can turn out to be, you know, tangent. We used tangent earlier. It can be Pythagorean. So I have, what, 11 minutes? I want to try and set up the last problem, just so you can kind of see a problem that's very different than everything we've seen so far, to kind of, again, stress that these are all unique. A runner sprints around a circular track which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. Her friend is standing at a point 100 meters from the center of the track. How fast is the distance between the two changing when the two are exactly 120 meters apart? Try and visualize this. Circular track, person running around it, a friend standing nearby watching. If they were connected to each other with a rope, what this question is asking is how fast that rope is moving out of one of the person's hands as at a specific instant. You want to see the picture? The animation? You haven't had enough time to think about it? Runner, circular track, observer. Remember, the circular track has a radius of 50 meters, right? 50 meters. How far away was the person watching? 50-meter track radius. The person is 100 meters away. Does it matter where I put this person? Like, could I put the person 100 meters like there? That's 100. Or here, 100 meters, right? Couldn't that person be anywhere as long as they're 100 meters away? I only put the person here kind of like on the x-axis because it just makes sense to put that person somewhere convenient, right? Not some arbitrary weird angle, just off to the side somewhere. We could always rotate this any way we want and it would be the same picture. So here we go. Person's running around the track, right? At some point in time, they're 120 meters apart. So when, right? We know the distance from here to here is 100, right? Meters. So would you agree that if we're interested in what's happening when they're 120 meters apart, 120 meters apart, that would have to be somewhere on this side, right? It couldn't be over here. Like the runner would have to be somewhere on this side for it to be 120. And wouldn't it happen in two different places, here and maybe here somewhere? There'll be two different locations where they're 120 meters apart. At one location, again, imagine that they had a rope between them. At this location, if the runner is going this way around the track, then the rope would actually be coming out of this person's hand, right? The person watching, if there was a rope, as the runner, because the runner would be kind of going away from them a little bit, so the rope would be coming out of their hand. Whereas opposed to at the bottom, now they're getting closer together, so the rope would be coming towards them. This problem does not specify which situation we're supposed to look at. It's just saying when they're 120 meters apart, how fast is the distance between them changing? That's all it says. Running around, running around, running around. I'm gonna cheat. I'm gonna copy this. I'm gonna take it over here. I'm not gonna draw my general picture and stuff over there. I'm just do it right here. I'm gonna try and draw a general picture now. Of course, I'm interested in knowing the distance between the two, right? That's what I'm interested in, is how fast is that changing? So I better label that. What should I label that? I don't care.
A.
A? Okay, we'll call that distance A, lowercase a. Is that all right with you? So I kind of know already I want dA dt. I want dA dt. I want to know how fast the distance between them is changing. I also know that I want it at exactly the moment that A is 120, right? At exactly the moment that that distance between them is 120, I want to know how fast it's changing. What am I given? What am I given? I'm given the speed of the runner around the track, right? 7 meters a second is the speed of the runner around the track. Ooh. What the heck? How are we gonna do this? See, it's not, the runner is running around a circle, not a straight line. So I can't call this like X or something and then say dx dt is 7. This is an extremely difficult problem, right? It's the last problem I'm gonna do. So, and I don't have time to finish it, so.
Does that have to do with something with a tangent or no? Like a tangent?
We could, well, it has something to do with,
Not the tangent, the other one that touches 2 points. I don't know.
Secant?
Secant line,
Yeah.
maybe. No.
I'm not gonna say we couldn't do it that way, but I don't, let me draw it for you, okay? Let me draw it, and then, because I only have 4 minutes, I'm gonna set it up for you. Do you all agree that the distance from here to here is 50, no matter what? No matter where she is on the track, that distance, wherever she is 50 all the time, yes? And do you also
Yes.
agree that the distance from here to here is 100, no matter where she is on the track all the time, right? That's a triangle. It's not a right triangle, but it is a triangle, yes? Here's the part of the problem that most people won't get until they see someone do this. This right here, this angle theta, right, will change, won't it? It'll change as she runs around the track. Theta is going to change. Do you think you can tell me how fast the angle is changing? I mean, imagine you're standing in the center of the track watching a person run around, right? You're standing in center track. If you're watching them run around and they're going the same speed the whole time, right? Then you're going to be rotating at the same speed the whole time, aren't you? If you're at the center of the track, I'm getting dizzy. Do you all understand?
Yes.
Yes.
Okay.
Yes.
So somehow her, her linear speed on the circle, somehow we need to convert that to her angular speed. Telling me that she's moving at 7 meters per second around the circle should be enough information for me to figure out how fast the angle is changing. The angular speed is d theta dt, right? It's the rate at which theta changes with respect to time. That would be my given. And so all I would need is a formula that relates theta to A off of this picture. We're almost out of time. Can anybody, I'm not showing you how to do this problem. I'm trying to get you set up for it. Can anybody think of what equation out there would relate the angle of an arbitrary triangle, this is not a right triangle, an arbitrary triangle to the side that's opposite of it if you knew the two other sides? Pre-cal, 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 pre-cal.
Would it be tangents?
That's only if it's a right triangle.
Oh,
Would be
Not a right
Pythagorean
triangle.
theorem.
What's that?
Pythagorean.
Arctangent? No.
No, how about because it has to equal 360, it has to do with the sides equaling the degrees.
In our formulas for trig, pre-cal, there's an arbitrary triangle. This is not a right triangle. This is just an arbitrary triangle. Okay. And with an arbitrary triangle, we have two main formulas, the law of sines and the law of cosines. The law of cosines creates a relationship between all the sides and one of the angles. Law of cosines creates a relationship between all of the sides, side little a, little b, little c, and one of the angles. That's exactly what we would need here, because we have all the sides, right? Well, there's one side we don't know, A, but we have the other two sides and we have the angle. And so we should be able to use law of cosines to create our equation. I've got to leave it here. I want you to do your best on the homework. We're done with 2.7 in terms of, I'm not going to do any more problems. This problem right here, I would never ask you necessarily on a test, okay? But I challenge you, if you finish your homework and you feel like you want something to finish off, this is a great problem to try and finish, because you still have a lot to do here. Angular speed needs to be figured out. You've got to set up the law of cosines. You've got to differentiate it. You got to be able to plug everything in, see how it goes. But that's it. Related rates, we'll start chapter 3 next time. All right, we're done with chapter 2. So everyone have a great weekend. And yeah, I'll see you.
Thank
Thank
you.
you.
Have a good night.
Good weekend.
Do your homework.
Speaking of professor,
Yes.
On Canvas, the due date the due date for 2.7 needs to be updated.
Yeah, I know. I've fallen so behind on that stuff. It's just ridiculous. I'm gonna do it right now.
Okay,
Yeah.
just wanted to tell you.
Yeah, no. Thanks for bringing it up. I mean, I realize that. Like I said, I was doing this whole thing where you turn in your homework to really trying to help motivate people. I don't know if it's had the effect that I was hoping it would, but let me see here. Handwritten homework 2.7. Whoa. Yeah. Okay, I got it. Thank you. Anyone else?
I think that is just me. So
Okay.
yeah, I think that's it. Unless the 3.3 also, but that's later.
Yeah, I'm gonna have to update that. Wait a minute. Hold on. Today's the
24th.
Yeah, so yeah, I think maybe next Thursday. I'll make it the following, just in case. There. I'll have to update a lot of these.
Because we were behind, correct?
Yeah, we're in it. Yeah, we're a little bit behind, but I'm going to make up time here with the 3.1 and 3.2. We're going to just blow through.
Yes, sir. Alrighty. Well, you have a good weekend, sir.
You as well. Thank you.